This is Lecture 7a in ECE 361, Probability for Engineers, Fall 2016, Part 1. In today's lecture, we'll cover two sections from the book. First, Section 3.5 on conditioning, and second, Section 3.6 on the continuous version of Bayes' rule. This first part of the lecture will cover Section 3.5, conditioning, and we'll have the following four subsections: conditioning a random variable on an event, conditioning one random variable on another, conditional expectation, and independence. Let's first start with conditioning a random variable on an event. So recall the total probability theorem, which we covered early on in our discussion, and there we talked about the idea of a partition of the sample space. Recall that a partition has two essential properties. First, no two subsets in the partition have any overlap. That is to say, every pair of subsets is pairwise disjoint, and every single outcome is in exactly one of the subsets, which is to say, if you take the union of all of these subsets, you get the sample space. Often we'll use the simplest possible partition, which is a single event A and its complement, A sup C. But when we were discussing discrete random variables, say x, we observed that the probability mass function for that random variable x, denoted little p sub x at x, that is the probability that the discrete random variable x takes on the value little x, can be seen as the sum of the conditional probabilities that x takes the value little x conditioned on the events AI, weighted by the probabilities that AI is true. And the motivation for considering the total probability theorem has always been the following: that we start with a complicated event, namely the probability that the random variable x takes value little x, and we simplify it with a larger number of simpler events and probabilities. In particular, if we know that AI is true, the idea is that if we choose the AIs correctly, we'll be more easily able to assess the probability that the random variable x takes on the value of interest little x. Okay, so then in the case of continuous random variables, the exactly analogous concept holds. The continuous version of the total probability theorem states that given a continuous random variable x with a probability density function little f sub x, the probability density at little x is found by summing over all possible events in the partition a1 through an, and for each such I, we evaluate the conditional probability density function of x given that AI is true at the target value little x, and weight that probability density function by the probability that AI is true. Again, recall from last lecture that where we talked about the interpretation of the conditional probability density function little f sub x given AI as roughly the probability per unit length conditioned on AI being true. Let's do an example to illustrate these concepts. The idea in this example is that the metro train is arriving every quarter hour, and in particular at 7 a.m., 7:15 a.m., 7:30 a.m., 7:45 a.m., etc. Because of variability in your schedule, you arrive every morning at the train station uniformly between 7:10 and 7:30, a 20-minute window. So clearly, under that assumption, you're either going to catch the 7:15 train if you are arriving between 7:10 and 7:15, or you're going to catch the 7:30 train if you arrive strictly after 7:15 and between then and 7:30. And so we can define the natural random variable y, which is going to be the waiting time to board the train, and the question is to find the PDF of the time to board the train. Now this is a natural question in which to use the total probability theorem precisely because it's going to be difficult without conditioning to get at the waiting time distribution, precisely because we want to first understand which train we're waiting for. So we'll define the event A that your arrival time x, which is the minute at which you arrive, minutes after 7. So let's first define that random variable x to be uniform between 10 and 30. Y will be the waiting time to board the train. Now again, note that y is between 0 and 15, because if you arrive between 10 and 15 minutes past the hour, you'll wait at most 5 minutes. If you wait between quarter after and 30 minutes past the hour, you'll again wait at most 15 minutes. So let's define the event A as the arrival time x being in the interval 10 to 15, and its complement then is that the arrival time x is between 15 and 30. Note that A and AC form a partition of the sample space. So now we want to say conditioned on A, meaning conditioned on arriving between 10 and 15 minutes after the hour, we know that Y, the time to wait for the train, is going to be uniform over 0 to 5 minutes. Conditioned instead on a complement, namely arriving between 15 and 30 minutes after the hour, the waiting time is itself going to be uniform over 0 to 15 minutes. So here's the form that the total probability theorem takes in this context. The PDF of the waiting time y at value little y is found by weighting together the conditional density functions little f sub y given a and little f sub y given a complement, with weights corresponding to the probability of a and the probability of a complement. Now clearly the probability of a is 1/4 because there's a 20-minute window and a holds true when you arrive in the first 5 minutes, which happens with the probability 5 over 20 or 1/4. And thus, of necessity, probability of a complement holds probability 3/4. So what we've plugged in here is 1/4 probability of a times 1/5 conditional PDF given a plus 3/4 probability of a complement times 1/15 the conditional probability density of y given a complement. And you put those together, you get 1/10 for y in the first 5 minutes, and the same argument gives you 1/20 for y between 5 and 15. Okay, moving on to the next topic, conditioning one random variable on another. So recall when we were discussing discrete random variables, we defined the conditional probability mass function for a pair random variables x, y as p of x given y as the ratio of the joint distribution over the marginal. In particular, the conditional distribution of x given y is the joint distribution of x and y over the marginal for y. The exactly analogous formula holds in the case of continuous random variables, replacing probability mass function with the probability density function. In particular, the conditional distribution of the random variable x given the value for the random variable y is the ratio of the joint distribution of the pair x and y over the marginal probability density function for y. Now, last time we talked about how to marginalize the joint distribution fxy by integrating over all possible values x to get the marginal for y. And now we're going to use that to see that this is in fact a bona fide distribution. In particular, when I integrate this conditional distribution over all possible values x, then I substitute in the ratio of the joint over the marginal. This is an integral with respect to x, and so the denominator is independent of x and can be pulled out. And now, since I'm integrating the joint distribution over all possible x, I know from this equation up here that that equals the PDF for y. And so then you see I'm going to have the ratio of the density of y over the density of y equal to 1. Let's do an example. So in this example, we're considering a dartboard. A dartboard is simply a circle of a given radius, r, and when we throw the dart, we suppose, because we aren't very good at darts, that all points are equally likely. But we are guaranteed to hit the dart board itself, and so in fact the point we get, which we represent by the random pair x, y, is uniform over the circle. That's what it means to be uniformly likely for all possible points. In particular, the joint density of the pair x, y is 1 over pi r squared, the area of the circle, for any pair x, y satisfying the distance from the origin which represents the bullseye, being less than r squared. Make sure you understand that this is the equation that constitutes a pair xy being in that circle. Any other point has probability density 0. Our goal is to find the conditional distribution of the x-coordinate of the position of the dart given knowledge of the y-coordinate. So if you picture the circle, you should be able to see that as the y-coordinate, represented by little y, increases towards r or decreases towards negative r, that the allowed set of values for x is becoming narrower and narrower. And we want to compute exactly what that is. So because we know that the conditional distribution equals the joint over the marginal, our approach is to first find the marginal PDF for y. And we're going to do that by integrating the joint distribution over all possible values of x. So we substitute in the form of the uniform distribution, which is simply the constant 1 over pi r squared, and the support for that pair of random variables, however, is the set of all pairs xy with distance from the origin less than or equal to r squared. Now, a simple recognition of this event shows you that if we're looking for pairs xy such that the distance less than or equal to r squared for a given x, that's equivalent to x being less than or equal to, or being between negative root r squared minus y squared and positive root r squared minus y squared. Simply solve this equation here for x. And of course, this is the integral of the constant 1 with respect to x, and so its integral equals the difference of the values, which is twice root r squared minus y squared over the denominator pi r squared. And that's true for any y in the support, and of course, the set of all y's in the support are all y's whose absolute value is less than or equal to r, the radius of the board. This picture may help you see some of those arguments more clearly. Here's a sketch of the xy plane with the bullseye at the center, our border of our circular board here at radius r. And if we suppose that we are at some radius y, then we want to find the distribution of values of x. Sorry, I said that incorrectly. If we suppose that the y-coordinate of the dart is at some value y, then we want to find the distribution of the possible x-coordinates, which is this segment over here. So to do so, we use the equation that the conditional density f of x given y is equal to the ratio of the joint density f of x comma y over the marginal for y. And now we just substitute in what we derived on the previous slide. In particular, we were given that the joint distribution is 1 over pi r squared, and we derived that the marginal distribution was 2 over pi r squared root r squared minus y squared. And although this expression depends upon r and y, it's important to observe it does not depend upon x, other than to say that the set of possible values for x also depend upon r and y. But what it means then is that the conditional distribution for x given y is uniform over the segment stretching between negative root r squared minus y squared and positive root r squared minus y squared. And of course, then that constant is equal to 1 over the width of that interval, namely 2 times root r squared minus y squared. So what we've just shown is the rather intuitive fact that if I tell you any point on the dartboard is equally likely, and then I tell you that the y-coordinate is some height y, then we've shown that the distribution of the x-coordinate, given that knowledge, is uniform over this segment of feasible y values. So we want to talk a little bit about how to interpret the conditional probability density function, and we've been appealing in the last lecture to this notion of a small rectangle or small square on the xy plane at some point xy with side lengths delta. So now what we want to do is suppose we want to interpret what is the conditional probability that the continuous random variable x lies in a small interval, namely the interval x to x plus delta 1, given knowledge that the random variable y is in the interval y to y plus delta 2. So you want to picture the xy plane, consider the point x comma y as the lower left-hand corner of a rectangle with x coordinate length delta 1 and y coordinate length delta 2. And we're asking what is the probability that x lies in the interval x to x plus delta 1, given knowledge that y is in the interval y to y plus delta 2. Now, by definition of conditional probability, probability of A given B is always probability of A and B over probability of B. In this context, when I apply that definition, I put both of these events in the numerator, the probability of x being in the interval x to x plus delta 1 and y being in the interval y to y plus delta 2. That is, this is the probability of the event that the pair xy is in the square with lower left-hand corner x and y and widths delta 1, delta 2. And the denominator is simply the probability that the random variable y is in the interval y to y plus delta 2. Now, as we've talked about before, whenever we have these situations where we have a density or a probability or a joint probability, and these intervals are small, then we can interpret that as the joint density times the area or the length of the interval or square. So in the numerator, this, for sufficiently small delta 1 and delta 2, is the probability density function, the joint probability density function at the pair xy times the area of the rectangle. And in the denominator, the probability that the random variable y is in the interval y to y plus delta 2 is roughly equal to the density of y at little y times width the interval delta 2. And now you see that the delta 2's are going to cancel, and what you're going to be left with then is the ratio of the joint over the marginal times delta 1. And of course, the joint over the marginal is the conditional distribution. And so putting it all together, we have the consistent result with our other interpretations that the probability that the random variable x sits in some interval of width delta 1 around x, given knowledge that the random variable y takes value little y, is equal to the conditional probability density function f of x given y at x given little y times the width of the interval delta 1. In other words, that conditional distribution, that conditional probability density function is again probability per unit length for the random variable x around the point x, given that the random variable y equals y. Let's do an example. In this example, we're measuring a vehicle's speed, say through a police radar detector. So the vehicle's speed is itself a random variable, and we assume that it's exponentially distributed with parameter lambda equal to 50 miles per hour. Now recall that for the exponential distribution, if the parameter is lambda, then the expected value of that random variable is 1 over lambda. So our parameter is going to be 1/50th in order to have a mean value of 50. So the police radar sees the speed, but it's corrupted by noise. And this is a very common model to use in many scientific and engineering applications. In particular, the police radar measurement is a random variable y that equals the given vehicle speed plus an error term. That error term is, and again this is very common, assumed to follow a normally distributed random error with zero mean and a standard deviation of 1/10 of the speed of the vehicle. And on the next slide we'll translate that into notation. Let's make sure we understand that. Y is the police radar measurement, and the police radar measurement is the signal, which is the vehicle speed, x, plus an error term. That error term has zero mean and a standard deviation of 1/10 of the speed of the vehicle. And our question is to find the joint probability density function for the pair xy, x again being the vehicle speed, y being the measured speed. Okay, so again, what we were told is that x is exponentially distributed with mean 50, which means it has parameter 1 over 50. And now if what the model tells us is that if we were to observe a particular value of the vehicle speed x, then the vehicle speed that's seen by the radar would be that value x plus a noise term. And that noise term is normally distributed, has zero mean, and has a standard deviation equal to 1/10 of the measured speed. Now, if I take a constant x and I add to it a normally distributed random variable with zero mean and standard deviation x over 10, then of course all I'm doing is creating a normally distributed random variable with mean x and standard deviation x over 10. So now we know the distribution of y given x, and we write that here. The probability density function for the measured speed y given the actual speed x is the normal distribution, recognize this form from last lecture, where the standard deviation, often denoted by sigma, is now x over 10, and here's an x over 10 squared, and the mean is x, often denoted by mu in our previous notation. So in order to find the joint distribution, f of x comma y, we use the fact that the conditional distribution is the ratio of the joint over the marginal, or rearranging, the joint distribution is the product of the marginal times the conditional distribution. And those are the two things we know. We know the marginal distribution on the vehicle's speed, and we know the conditional distribution of the measurement given the vehicle's speed. So now here I've just plugged in the marginal distribution for the vehicle's speed, and here I've plugged in the conditional distribution for the measurement given the vehicle's speed. So just to make sure things are very concrete, here is the probability density function for the actual vehicle speed, little f sub x. Here are three different values of the conditional distribution for three different values of x. Remember, x is the true speed and y is the observed speed. So if I observed x to be 100, here is the distribution f of y given x, normally distributed with that mean. If I had observed x to be 300, then here's the distribution of y given x. If I'd observed x to be 500, here's the distribution of y given x. And finally, this is an xy plane contour plot of the probability density function over the interval 0 to 5, 0 to 5, or actually 1 to 5, 1 to 5. And the same plot shown a little bit differently as a 3D plot shown here, where this is the x-coordinate, this is the y-coordinate, and this is the joint density f of x comma y. Okay, our third subtopic, conditional expectation. And you'll recall we saw formulas like this, the ones here on this slide, last time when we talked about discrete random variables and their conditional expectation. So the formulas are the same. All we've done is we've replaced the sums with integrals and the probability density functions, or probability mass functions with probability density functions. All right, so first formula states that the expected value of a random variable x, given knowledge that an event A is true, is going to be the formula you would come to expect, namely, we're going to integrate over all possible values of x, and we're going to multiply x by a probability density function, integrated over all x. Now, what probability density function is appropriate? Well, naturally, it's the probability density function for x given knowledge that A is true, because that's what's assumed to be true out here. If we take the case where the event A is the event that a random variable y takes some value little y, then the expected value of x, conditioned on the random variable y taking value little y, is found by integrating over all possible x, and we multiply x by the suitable probability density function, which in this case is the conditional distribution of x, given that y equals little y. And again, we've seen these things very many times by now. If instead of just wanting to know the expected value of x, I wanted to know the expected value of some function of x, say g of x, then the expected value of some function g of x, given knowledge that the event A is true, is found integrating over all possible values of x. For each value of x, I evaluate g at x and weighted by a suitable probability density function, which again in this context is going to be the conditional probability density function of x given A. And finishing up the thread, condition on the event that the random variable y equals little y, the expected value of the function g of x, under that assumption, is the integral over all possible values of x. For each such value of x, I evaluate g at x and weighted by the conditional probability density function of x given y. And again, this is the total expectation theorem. We saw the same formula in the context of discrete random variables, and here they are again. So again, we have a partition of the sample space, A1 through AN, and we assume that each element of the partition has some probability P of AI. And now we want to find the expected value of some complicated random variable X. And if that's too hard, what we can do is we can partition using A1 through AN, and then find the conditional expectation of X given AI using the formula on the previous slide. So all the total expectation theorem says is that the expected value of X can be found by summing over all values of I and compute the expected value of X given that AI is true, weighting it by the probability that AI is actually true. Similarly, I could condition on all possible values of a continuous random variable Y. So if I want to know the expected value of a complicated random variable X, then if that's too hard by itself, I can always condition on the value of a related random variable Y, and then for all possible values that Y might take, I look at the expected value of X given that capital Y equals little y, weighting it by the probability density function for Y. And this expression right here, this conditional expectation, is precisely what we provided the formula for on the previous slide. And of course, I can extend both of these ideas to functions g of x and y. So in this setting here, I'm looking at the expectation of some function g of random variables x and y, given knowledge that the random variable y takes value little y. So what am I going to do? I'm going to integrate over all possible values of x, which is the remaining unknown, evaluate the function g at the pair little x, little y, and weight it by the conditional probability density function x given y. Hopefully you're starting to see the internal coherence of all of these expressions. Finally, if I want to find the expectation of some function g of a pair of random variables x comma y, if that's rather complicated, I can first condition on the random variable y. And that's what I do here. I consider all possible values of y, and I evaluate the expected value of the function g of the pair xy given knowledge that the random variable y equals little y, weighted by the probability density function at y. And now this expression right here is precisely what this equation tells you to do. So in effect, what you're doing is you're integrating over all possible values of x and y, and you're going to evaluate the function g at the pair xy, ultimately weighting it by the joint density function f of x comma y. Now that joint density function might be best expressed as the product of the marginal times the conditional, and that's the whole point of this derivation here. Let's do an example. In this simple example, we have a random variable x, and x has a rather simple distribution. It's piecewise constant, which is to say that over the interval x between 0 and 1, it's uniform with probability 1/3. And over the interval x between 1 and 2, it's uniform with probability 2/3. So here's a sketch of the probability density function for the random variable x. It's 0 for x less than 0, 1/3 for x between 0 and 1, 2/3 for x between 1 and 2, and 0 for x greater than 2. We'll come back to the rest of the figure in a minute. The goal of this question is to find the mean and the variance of the random variable x. And as we'll see, the natural thing to do is to condition on the event A, where A is the event that x is in 0, 1, and naturally its complement is the event that x is in 1 to 2, and observe by the support of x that forms a partition of the sample space. Okay, so here is the setting. And again, we say we're going to consider A as the event that x is in the interval 0 to 1, its complement A sup C, the event that x is in the interval 1 to 2. If we go back and look again, it should be clear that the probability that x is in A, which is obtained by integrating the PDF over 0 to 1, is going to be the area under the PDF from 0 to 1, which of course is height 1/3 times width of 1, or probability 1/3. Likewise, the probability of A complement is obtained by integrating the PDF from 1 to 2. In this case, that integral, which is the area under the curve, is the area of this rectangle, which has height 2/3 times width of 1, or probability of A complement is 2/3. And that's what I've written here. Probability of A is 1/3, probability of A complement is 2/3. And now what I can do is I can derive the conditional distribution of the random variable x given a, and the conditional distribution of the random variable x given a complement. Given that a is true, the probability density function is going to be equal to 0 for x between 1 and 2, and given that a complement is true, the probability density function is going to be 0 for all x between 0 and 1. So what I'm doing here is simply using the equation we've seen before, that the conditional probability density function at x given a is the ratio of the unconditional probability density function, which has value 1/3, over the probability of a, which is also equal to 1/3. So I get 1/3 over 1/3 equals to 1. And all that means is that condition on a being true, x is uniform over interval 0 to 1. And the same thing is true here. The probability density function for x given a complement is the ratio of the unconditioned probability density function, the marginal for x, which is equal to 2/3 for all x in 1 to 2, divided by the probability of a, which is also equal to 2/3. I get 2/3 over 2/3 equals to 1. Again, all it says is condition on a complement, the distribution of x is uniform over 1 to 2. And now I can use the formulas for the expectation of the random variable x given a and the expectation of the random variable x given a complement. In particular, x integrating from 0 to 1, x times the conditional density f of x given a gives me x, remember this is 1, times when that integral evaluates to 1/2. And likewise here, when I have x times this conditional density, which again equals 1, this equals 3/2. And that's, so if you see that the conditional expectation of x given a is 1/2, conditional expectation of x given a complement is 3/2, that's quite intuitive from our graphical picture that given knowledge that the x is in this interval 0 to 1, we know it's uniform over that distribution, and therefore its expected value given a is going to be in the middle of that segment. Likewise, given knowledge that a complement is true, we know that x is uniform over this segment 1 to 2, and therefore its expected value given a complement is going to be in the middle of that segment, namely at 3/2. Finally, now we can put those things together by using the total expectation theorem. Expectation of x is the expectation of x given a times the probability of a, plus expectation of x given a complement times the probability of a complement. Remember, this was 1/2, this was 3/2, this was 1/3, this was 2/3. Put that all together, you get 7/6. So we see that the expected value of x is just a little bit over 1. And that's to be expected given the fact that the higher mass is above 1 on the support 0 to 2. Now to find the variance, we're going to use our tried and true formula where we first find the expected value of x, then we find the expected value of x squared, and then we look at the variance of x as the difference of the expected value of x squared minus expected value of x quantity squared. So we're going to find expected value of x squared given a, and you think of this as your function g of x. So now what we're doing is we're going to evaluate by integrating over all possible values of x. G of x here is x squared, and we use the appropriate conditional density of x given a. That translates to x squared times this conditional density, which again was 1, and that turns out to equal 1/3. Similarly, expected value of x squared given a complement, again integrate over all possible values of x. This is your g of x, this is your conditional distribution of x given a complement this time. You substitute in the form of that conditional distribution, which we computed on the previous slide, evaluate the integral, you get 7/3. And then I can use, again, the total expectation theorem. Expected value of x squared is the expected value of x squared given a times probability of a, plus expected value of x squared given a complement times probability of a complement. Again, we just computed e of x squared given a, e of x squared given a complement, so that's where the 1/3 and the 7/3 come from. And we got 1/3 and 2/3 for probability of a and probability of a complement on the previous slide. Put it together, you get 15/9. Finally, we'll use our formula variance of x is expected value of x squared, or 15/9, minus expected value of x quantity squared. 7/6 squared is 49/36, and this becomes 11/36. Okay, so make sure you study this example to see the thread of the ideas. Our last subtopic in section 3.5 is independence. And we've already touched on some of these ideas in the past in the setting of the discrete random variables and in the setting of events. So let's review. So our definition is going to be that two continuous random variables are independent if their joint distribution function f of x comma y is equal to the product of their densities f of x times f of y for all x and y, and I actually don't need that equation there. Equivalently, that the probability density of x given knowledge of y is equal to the probability density of function of x for all x and y. If that's true for all such x and y, then we say that the pair x and y are independent. And this is directly analogous to the definition of independence for discrete random variables. In that setting, we'd said that x and y are independent if the conditional distribution, the conditional probability mass function of x given y, is equal to the marginal distribution. In other words, knowledge of y has no effect on the probability of x. If that's true for all x and y, then again, x and y are independent. And both of these, the continuous notion of independence and the discrete notion of independence, are directly analogous from the original concept that we defined, which is independence of events. There we'd said given events A and B, we say A and B are independent events if the probability of A given B equals probability of A. That is, knowledge that B is true does not affect the probability that A is true. Okay, so the definition should not be too strange. Here's a simple example. Let's suppose that x is normally distributed with parameter mu x and sigma x, and y is normally distributed with parameters mu y and sigma y, and suppose x and y are independent. Then their joint PDF, f of x comma y, is the product of their marginals, f of x times f of y, and I substitute in the form of the normal distribution PDF for these parameters and multiply them together and simplified by adding up the exponents. So what independence allows you to do often is to multiply. So let's see exactly how that happens in the context of continuous random variables. So we have a pair of independent random variables, x comma y, and we chose subsets A and B so that we're interested in the event, the probability of the event that the random variable x is in the set A and the random variable y is in the set B. So I want to do that, then I know I can always get answers to such questions by integrating over all possible pairs of x and y such that x is in A and y is in B, where I'm integrating the probability density function f of x comma y. Now, because the pair of random variables x and y are independent, I can always replace this joint probability density function with the product of their marginals, f of x at x and f sub y at y. And when I do that, I'm allowed then to split up the integral so that I end up with the product of the integral over x and a of the density and times integral over y and b times the density for y. In other words, this is going to be the probability that x is in A times the probability that y is in B. If I'm interested in events of the form that x is less than or equal to some value little x and y is less than or equal to some value little y, then what I'm effectively doing is evaluating the joint cumulative distribution function, capital F sub xy. Recall that capital F sub xy at little x comma little y is shorthand for the probability that the random variable x takes a value less than or equal to little x and the random variable y takes value less than or equal to little y. If x and y are assumed to be independent, then using the descriptions and definitions we've just been discussing, that joint CDF is going to be the product of the marginal CDFs. Using the same rule here, the probability that x is less than or equal to x and y less than or equal to little y is the product of the probabilities that the random variable x is less than little x times probability that random variable y is less than little y. And this, of course, is simply the product of the CDFs at x and y respectively. These same notions allow us to express that expectations of functions of the form g of x times h of y, where x and y are independent random variables and g and h are arbitrary functions, is going to equal the product of the expectations. To see how that happens, let's consider the definition of this quantity. Well, we're going to integrate over all possible values for x and y, and for each pair little x little y, we evaluate the argument g of x times h of y, and we weight that by the probability density function. But since x and y are independent, we can replace that probability density function with the product of the marginal densities and therefore I can factor this integral as the product of the integral over x times the product of times the integral over y. And this right here is, of course, the expected value of g of x, and this right here, of course, is the expected value of h of y, giving e of g of x times e of h of y.